In this video, we're going to look at a couple ways to prepare some carboxylic acid derivatives other than the interconversion through nucleophilic acyl substitution that we'll cover later. One very important reaction is the conversion of a carboxylic acid to an acid chloride, and this uses thionyl chloride. You're not responsible for the mechanism of this. You can look it up in the book if you're interested, but just recognize that carboxylic acid plus thionyl chloride gives an acid chloride. When we were talking about electrophilic aromatic substitution and Friedel-Crafts acylation reactions, we always talked about acid chlorides rather than acid bromides, for example, simply because this is such a straightforward way to access an acid halide. Carboxylic acids can also be converted to esters in a couple different ways. If this is treated with base, then the base can grab off the acidic proton, and the carboxylate can act as a nucleophile. So it can share its electrons with the carbon, pushing away bromine as a leaving group, giving an ester. This is a very limited reaction. This can only be done with methyl or primary alkyl halides. There's another much more general approach toward making esters, and that's shown here as the Fischer esterification. Typically, with the Fischer esterification, you have your carboxylic acid plus an alcohol in the presence of HCl or sulfuric acid, for example, and this will give the ester plus water. Because this is an equilibrium reaction, it's important to push the equilibrium in the direction that you want. In this case, we're looking at a simple acid and a simple alcohol, but if you had a complex and valuable acid and you had a simple alcohol, then you would use a huge excess of the simple alcohol to push the equilibrium to the right. Or if your alcohol was something that was complex and valuable, then you might choose to use a simple acid such as acetic acid in order to push the equilibrium to the right. So at the end of the reaction, you would have to isolate your ester, separate it from your excess alcohol or excess acid. The mechanism of the Fischer esterification is especially important in part because investigations of this mechanism led to an understanding of a lot of the nucleophilic acyl substitution reactions. So we're going to spend some time focusing on the Fischer esterification. In the carboxylic acid chapter, we looked at just a couple of examples of Fischer esterifications. So here we have benzoic acid plus methanol in the presence of sulfuric acid can form methyl benzoate. This is called isopentyl alcohol plus acetic acid can form isopentyl acetate, which is banana oil. If you look at the ester product, these atoms are clearly from the carboxylic acid, and these atoms are from the alcohol, but an important question is the source of the oxygen. Is that from this oxygen, or is it this oxygen? Identifying which oxygen provides information about the mechanism of the reaction. One approach toward trying to understand a reaction mechanism is to use some kind of labeled reagent. So this might be a radiolabel, and then one would try to separate the products and then determine where the radiolabel is in this product or in this byproduct. Depending on which atom we're labeling, we've got radiolabeling, we could have labeling with something that would be NMR active, so there's a number of different ways that this could be done. If this reaction was carried out where benzoic acid is treated with methanol with labeled oxygen, we can think about a few different possibilities. One option is maybe this is an SN2-like reaction. So it's kind of like an SN2, where this is the nucleophile, and this shares electrons here, pushing away water as the leaving group. If this is the mechanism, and I'm not showing all of the steps, but if this is the general mechanism, then we would expect to have the radiolabel in the water. Another possibility is that the alcohol is the nucleophile and it shares electrons with the carbonyl carbon. And in that case, this oxygen would be the one that came from the alcohol, and so the radiolabel would be with the ester. What was discovered experimentally is that the radiolabel was associated with the ester. So that does not support the SN2 type of reaction. It does support the nucleophilic acyl substitution mechanism. And this is just one example of a lot of experimental work that was done to try to understand the mechanism of this reaction. It's important to keep in mind that the mechanism of a reaction can never be proven. There may be a lot of support for a particular mechanism, but it's always possible that somebody can design the experiment that disproves a particular mechanism. But what we have here is a commonly accepted mechanism, and in general, chemists think about the Fischer esterification as occurring in two stages. Part 1 is the formation of the tetrahedral intermediate, and then part 2 is the dissociation of the tetrahedral intermediate. So for this overall reaction, let's work through the formation of the tetrahedral intermediate. So whenever we have alcohol and H+, we're going to have the protonated alcohol. This mechanism, this proposed mechanism, begins with an acid-base reaction where the carbonyl oxygen can grab a proton from the protonated alcohol, putting these electrons back onto the oxygen. So now we have our protonated acid, and we get back a molecule of the alcohol. In the next step, the alcohol acts as a nucleophile, so this is a nucleophilic addition step, where the oxygen shares electrons with this carbon, pushing these electrons up onto the oxygen, and that gives us this intermediate. Next, we have another acid-base reaction where the alcohol can grab off this proton, putting these electrons onto the oxygen, giving us the tetrahedral intermediate. So the formation of the tetrahedral intermediate is an acid-base reaction, nucleophilic addition, and then another acid-base reaction. That's part 1. Now part 2 is the dissociation of the tetrahedral intermediate. So this is the structure from the end of the last slide. What happens next is that one of these OHs can grab off a proton from the protonated alcohol, pushing these electrons back onto the oxygen, giving us this protonated species. Now it doesn't matter whether it's this one or this one, and it's also possible that this oxygen is the one that grabs off a proton. What you'll notice though, if you go back to the previous slide, is that if this grabs a proton, we're just going backwards. And that is going to happen because each of these is an equilibrium step. And so the reaction goes forward and in reverse. So after this particular acid-base reaction has happened and either one of these OH groups has been protonated, then the next step is an elimination, where these electrons come back in here to reform the double bond, pushing away water as a leaving group, giving us this carbonyl, which is still protonated, but now we are connected to the OCH3 group instead of over here we had OH. And then finally we have one more acid-base reaction where the methanol can grab a proton from the protonated ester, putting these electrons back onto the oxygen, giving us our final product. So this mechanism overall is nucleophilic acyl substitution, and it's also often referred to as nucleophilic addition elimination. because formation of the tetrahedral intermediate happens through the nucleophilic addition, and then the dissociation of the tetrahedral intermediate happens during the elimination. Now, it's also important to check our proposed mechanism and make sure that it is consistent with the experimental results. Remember when I talked about the isotopic labeling where we had our methanol was labeled? Well, this oxygen is the one that came from the methanol, and so that is still here, that is still here, and that is still here. And so the color coding was deliberate because this oxygen is the one that came from the methanol. And so this is what we would get based on the radio-labeled studies, and so those experimental results are consistent with this proposed mechanism. So here we looked at the formation of esters, and we also got an introduction to nucleophilic acyl substitution. In our next section, we're going to focus on nucleophilic acyl substitution as a way to interconvert between different carboxylic acid derivatives.